Welcome back again to this reading session. That shall be the fourth part as well as the last part, hopefully. The topic of the topic of today's reading session is electrically tuned fractional order temporal differentiator in silicon photonics. And authors are Afshin, Ahmadpour, Amir, Habibzadeh-Sharif, Faezeh, Bahrami, Chenaghlou. They are from all Faculty of Electrical Engineering, Shahid University of Technology, Tabriz, Iraq. So just to have connectivity, let me just read this abstract again so that we should have good connectivity with respect to previous reading sessions. Here, full wave analysis and design of an electrically tunable optical fractional order temporal differentiator based on an ultra-compact micro-ring resonator has been presented. Electrically tunability has been realized through free carrier dispersion effect in the resonator with PIN and PN junctions. The first order optical differentiator is realized based on the electrically coupled resonator without applying any bias voltages in the junctions. Also, fractional order differentiator with differentiation order alpha greater than 1 is realized by overcoupled resonator with the forward bias PIN and PN junctions. While fractional order differentiator with alpha less than 1 is realized by undercoupled resonator with reverse biased PN junction. The high performance of the design tunable optical differentiators and their high accuracy have been confirmed considering an ultra-fast Gaussian input pulse with short full width at half maximum of 6.3 picosecond. So this is the abstract. Now we have already covered this introduction section. Then this is the schematic of ultra-compact silicon all-pass micro-ring resonator based on PIN and PN. Then we have seen the transverse cross-section of micro-ring resonator and bus waveguide based on PIN and PN junction. So this is the electric field profile. There's some mathematical model, transfer function, and here symmetric and asymmetric modes, optical modes, and this intensity response and phase response of 3D FDT simulation, then optical frequencies versus intensity transmission and phase response, and so electrical tuning 2.3. Then we have gone through these other devices here. So now I think this is the last section, that is a 3. we start from here. Full wave analysis of temporal differentiator in the time domain. Figure 12 shows an ultra-fast Gaussian pulse in the temporal and spectral domains. Temporal and spectral domain with the spectral full width at half maximum of 71 GHz. On the other hand, figure 6a, 3 dB bandwidth of RR is equal to 143.13 GHz. That is broader than the full width at half maximum of the input Gaussian pulse. Therefore, the designed differentiator can operate properly. So let us see this figure 12, figure 15, 14, this is 13, and this is figure 12. So you can see normalized intensity of input Gaussian pulse. So this is temporal because time versus intensity, and this is so time domain, and this is frequency domain. This frequency versus normalized intensity. So time domain and frequency domain. Now full width at half maximum of this pulse is, intensity. So the U unit half power point, if it is, let's see, this half power point is this. If it is power, so power is equal to intensity per unit area. So half power point, so from here to here, so I think this should be total should be 6.3 picosecond. So unit is in this picosecond. So so you can see from here that much region is about 10 picosecond, and you can see here just an approximate. So you can see this is about 6.3 picosecond. You can easily say if this is say 10. So this must be about 6. Okay, so 6.3 picosecond. So the estimate, rough estimate, you can make out from this. Now coming to this optical frequency, what is the full width at half maximum bandwidth? So again, so this is power point. So you can see here from these to these, this should be approximately 71 gigahertz. 71 gigahertz. So since these are the terahertz, so from we can have a rough estimate. So here to here you can see 193.25 to 193.4. So this will be about point how much 40 minus 25. So 15.5 terahertz. So that was difference. So this is they are calculating as a 71 gigahertz. So in time domain, it is in pulse width, time unit, and in frequency domain, it is in the gigahertz. So this is the full width at half maximum bandwidth of this Gaussian pulse. Let us see this figure. I will see this figure 13. Output of first order differentiator based on all pass RRA without bias and mathematical differentiator with alpha is equal to 1 for Gaussian input pass. So this blue curve is mathematical one, continuous one, and this red dash curve optical differentiator. So both curves are overlapping only at this edge with the deviating. The deviation is 5% and alpha order is alpha is equal to 1. So it seems this is not a fractional order, it's simply 1. So 13. And now 14, output of a fractional differentiator based on APM RR for voltages of 0.65 volt. This is the A. This is for 0.6 volt. This is for 0.75 volt. In PIN junction, and output of mathematical function is 1.3 and 1.45. So this is PIN. And this is also PIN. So here alpha is equal to 1.3, here alpha is equal to 1.45. And deviation is reported here, say 1.3%, which you can see here. And here deviation is 5.8 from the mathematical differentiator. So This is with biasing only 0.65. So PIN, we can see it is positive voltage applied, so forward bias, it is in forward bias conditions. PIN to have more carrier plasma dispersion effect. And now coming to image figure 15, output of a fractional differentiator based on a all pass MRR for voltages of 0.65. So again, same voltage here 0.65 voltage, and here 0.75 voltage in PN junction. So earlier it was PIN, now it is a PN junction. So PN junction should be in reverse bias, that we have to see. The output of mathematical function differentiator for A 1.45 alpha and 1.48. A deviation is 6.4 and 28.2. But but here since voltage they are writing it positive, so that I have a little bit confusing. But what I know that PN junction gives more change in the carrier concentration with the reverse bias condition. Okay, nevertheless, that voltage must be applied positive, but internally it must be working as a negative potential for P type, P side. Now, now go to this. So, how are this figure 6a 143 point? Let us revise this also. Figure 6a. How this bandwidth of FRR 6.8. 6.8. Intensity, the phase response, B is phase response, this is the intensity response. And here we can see 3 dB bandwidth of this one is 143.13. So intensity 3 dB. So here we can see 3 dB here. This for this. So this must be 143.13 gigahertz. So this is what they are trying to tell, and that much is sufficient to cover this gigahertz range. So 71 gigahertz. The output of a differentiator with the two important properties, that are the proper ratio of the first and second peaks at the 0 point of differentiated pulse. The adequate matching of these properties between the optical and mathematical differentiator output confirms the operation of proposed structure as a temporal DIF. Also, in order to quantitatively evaluate deviation of the output of optical differentiator from those of mathematical counterparts, we define the deviation is equal to integration I all pass micro-refrigerator T minus I math T dt divided by Amir. So this is taking the only modulus of intensity of this is divided by the integration. So this is the deviation. The T there approximately equal to 10 times of full width and half width. That is the 60 picosecond. So since it was 6 picosecond. And I, APMR, R and I math are the normalized intensity output of the optical and mathematical differentiator respectively. According to section 2.2 and figure 6, the first order optical differentiator can be realized by critically coupled APMRR without applying any bias voltage in the PIL and PN junction. So 6 is without applying any voltage. So critically coupled. So under this condition, figure 30 shows the output of the first order optical differentiator that has a good agreement with that of the mathematical differentiator with a negligible deviation of 5%. According to figure 10 and 11 AB, in order to realize fractional order differentiator with order of 1 less than alpha less than 2, this alpha between 1 and 2, APMRR should be worked in its overcoupled region with applying forward bias voltage in the PIN and PN junction. So, overcouple can be done forward bias. So, alpha is greater than 1, less than 2. So, under this condition, figure 14 and 15 show the output of a fractional order optical differentiator that has a good agreement with those of the mathematical differentiator with deviation of 5.8% and 7.3%, 6.4 and 28%, 28.2%. However, according to section 2.3 and figure 8.11 AB, the APMRR with forward bias PN junction has not enough accuracy, especially for high applied voltages. On the other hand, with increasing the mismatch between the optical and the resonance frequency, the output of an optical differentiator does not drop to zero between its two peaks. So, deviation of the output of optical differentiator from that of mathematical counterparts increases. This phenomenon is shown in figure 15b, where the output of APMRR is not in a good agreement with that of a mathematical differentiator with deviation of 28.2. So 15 let us see 15p here, no division is there. Yeah, complete here to complete. So 28.2. 1.48. Therefore, the forward bias PN junction has not an acceptable potential to realize. Yeah, this is what I was trying to tell, that PN junction is more accuracy in reverse bias. The fractional order differentiator with high differential order, especially 1.422. Also, according to figure 11CD, the fractional order differentiator with fractional order differentiator with order of alpha less than 1 can be designed by undercoupled APMRR with applying reverse bias voltage only in the PN junction. So, under these conditions, figure 60 shows the output of a fractional order optical differentiator that have a good agreement with those of the mathematical differentiator with negligible deviation of 5.2 and 7%. Therefore, it can be deduced that APMRR based on the reverse bias junction can be modeled as fractional order differentiator with order of less than 1. So, this is what conclusion is good. So, this is as per expectations, because as I told that PN junction works efficiently in the reverse bias condition. Why? Because the carrier displacement takes more in reverse bias condition, because already there is a carrier because of a doping. So in reverse bias, carriers are displaced towards the depleted towards the majority side. So in this way, carrier is junction is void of the carrier. Change is maximum in reverse bias condition rather than the forward bias. Now conclusion. Full wave analysis and design of electrically tunable optical fractional order temporal differentiator based on an ultra complex APMRR was presented. Electrically tunability was realized using FCD effect, free carrier dispersion effect in the APMRR. Firstly, analysis and design of the first order optical differentiator based on the critically coupled APMRR without applying any bias voltage in the PIN and PN junction were presented without passing critically coupled. Considering the change in the carrier concentration of the silicon waveguide by applying different voltages, variation of the effective refractive index of the APMRR and consequently its resonance frequency as function of the applied voltage was investigated by electrical and Optical simulation. Intersected transmission and phase response in the frequency domain was shown and analyzed for various applied bias voltages in PIR and PN junction. It was shown that for both of the forward bias PIR and PN junction, by increasing the bias voltages, real part of the effective refractive index is decreased, while its imaginary part is increased. In contrary, for the reverse bias PN junction, by increasing absolute value of the bias voltage, the real part of the effective refractive index is increased, while its imaginary part is decreased. Reverse bias PIN junction cannot change significantly the effective refractive index. Therefore, the reverse bias PIN junction is not a useful candidate for design of the tunable differentiator. According to above mentioned results, the resonance frequency of the APMRR and its 3 dB bandwidth are changed, applying the reverse bias PN junction and forward bias PIN PN junction. Consequently, the operation region of the optical APMRR vary with the applied voltage. In fact, APMRR migrates from the critical coupling regime to the overcoupling regime using the forward bias PIN and PN junction, which leads to convert the first order differentiator to a fractional order differentiator with alpha greater than 1, where alpha is increased with increase of the forward bias voltage. As the same way, it migrates from the critical coupling regime to the undercoupling regime utilizing the reverse bias PN junction. Accordingly, the first order differentiator converts to a fractional order differentiator with alpha less than 1, where alpha is decreased with increasing of the absolute value of the reverse bias voltage. It should be emphasized that due to low accuracy of the forward bias PN junction for high applied voltage, it is not a good candidate to realize a fractional order differentiator with high differentiation order, especially for alpha 1.4 to alpha 2, less than 2. However, this forward bias junction realizes some order of fractional differentiator using low voltage compared with the PIN junction. As the way, considering similar low forward bias voltages for both junctions, higher order fractional differentiator can be designed by the PIN junction. Also, since the reverse bias PIN junction is not a good candidate for design tunable differentiator, our only proposed free carrier dispersion based device to realize tunable fractional order differentiator with order of alpha less than 1 is the reverse bias PN junction, which fortunately works efficiently. At last, an ultra-fast Gaussian pulse with short full width at half maximum of 6.3 picosecond was considered as an input of the temporal differentiator. Some simulation results are in good agreement with those of the associated formula in the mathematical model. As conclusion, the high accuracy of the presented result is a consequence of applying a full wave method based on powerful numerical techniques for the design of the electrically tuned ultra-compact APMRR as the tunable fractional order differentiator and analysis of the propagation of an ultra-fast optical pulse. So, declaration of competing interest, the author declared that they have no non-competing financial interest or personal relationship that could have appeared to influence the work reported in the paper. So, we thank member of Electromagnetic and Photonics Research Group at Shahid University of Technology for useful discussion. So these are the references. So thank you for attending this session. In this way, we are concluding today's session, which covers the reading of this article called Electrically Tuned Fractional Order Temporal Differentiator in Silicon Photonics. So this we have seen here. Optical computing based on integrated silicon photonics relies high order speed and ultra wideband optical processor. So see you soon. Thank you so much for attending this session.